Well, look what we got, Sam. We just have to write it all down. Here's hz. It's a constant times cosine kxx, cosine kyy. That's the f of xy we had last time.
Yep.
There's our traveling wave part. And this defines TE modes. Modes because for every m and n, you have different amounts of wavelengths crossways across the guide this way and this way.
So you would get some sort of funny patterns of E field and H field in the cross section. Is that correct?
That's correct. And we will compute from Hz in this case, Ex and Ey, Hx and Hy, and everything looks good. In fact, we know from our work previously and using back-cab rule and Maxwell that the sums of the k's are not freely chosen when you square them. You get kx squared plus ky squared plus kz squared equals question mark. Question mark.
Well, k is a vector, right?
K is a vector.
Well, then it should be obvious that it's k squared.
Oh, right. It's a sphere in k space. And how do we write k in terms of frequencies?
Should be that, just
It's
based on
that.
physical definition.
So look at this. We got a sphere. This is a sphere in k space. So we can solve for kz.
Oh, okay, yeah.
For each mode, kx and ky are these things. That means we can solve for kz.
Because these two are known based on the geometry.
Those from the geometry. So that means kz depends on the geometry. And the but, it's going to have a square root.
Yep.
And if the square root is negative, kz is purely imaginary.
Oh, so if you plug this into the traveling component, wait a minute, then you won't have a traveling component.
You won't have any waves energy going down the guide.
So there would be certain geometries and frequencies where wave can't travel on the guide.
Yeah, and the guide can't send energy back. And that's the mystery of cutoff.
Oh, mysterious.
We're just about done our construction if we look at cutoff. Then we can do wonderful things with our waveguides.